Let's do a final temperature problem, complicated when there's a temperature rise across a phase transition. So suppose you got water that's frozen and then it melts and then rises some more. That takes some energy to get it across that phase transition, or of course the one from liquid to steam is also another phase transition to consider, and that can throw a monkey wrench into the problem. So let's take a look at that. It's not hard, it's just a little bit more complicated. So what we got so far for temperature rise is that the amount of heat that you transfer can raise the temperature of some mass of substance by some delta T. And there's a constant in there called the specific heat. So there's this C constant that you have to look up for different materials. Well, when you cross a phase transition, you've got a couple more variables, and they're given the letter L, and we'll put an F on them or a V subscript there, and L for latent heat. So with a F on there, that is the latent heat of fusion, and you can also use freezing as a mnemonic for that F in there. And this is the latent heat of vaporization. And they're for phase transitions. So fusion would be going from solid to liquid, or vice versa, liquid to solid. You get that heat back out again. And then vaporization would be liquid to gas, and then gas to liquid would be the same number for that. And how you use it, so this is how you use this is how you relate heat and temperature change. To use these guys, it's much simpler. You still have the mass, and then you have the latent heat, and that's it. So basically from completion, if you're going at the freezing temperature, for example, if you're going from solid to liquid, this is how much heat you need. It just depends on the mass and this latent heat number. So that's pretty easy. Let's suppose you're looking at water. So here's a graph for water with temperature on the y-axis and heat added in some schematic fashion over here. And suppose you had ice at, and that would be below 0 Celsius. And as you add heat, you also raise temperature. So from somewhere off the graph, the line would come up at some slant like that. And then you hit the point where that ice goes liquid. Well, it doesn't change temperature until all of that solid has changed to liquid. And only then can the temperature go ahead and increase again. And so now this is the liquid state. And as you add heat, you gain temperature. And then you hit the vaporization temperature of 100 Celsius. And again, you've got a mixture of liquid and gas for a while. So here's the latent heat of vaporization for a while. And then finally you hit the gas phase and up it goes again at a slant. So on the slanty portions, then this is the formula you use. And then the specific heat you use will be different for ice, different for liquid, different for vapor. And then for the flat portions, in fact, that distance, that delta Q there, that is just mass times the latent heat of this much energy here would be mass times the latent heat of fusion. This one in here would be mass times the latent heat of vaporization from there to there. So it all comes out in energy units, which should be no surprise because energy is pretty nifty and energy is conserved. So that's kind of the behavior of water, and that's kind of what you have to watch out for in these final temperature problems. So let's do one based on the example that's in the book. So it's a final temperature problem. So that'll be the question. And they've got in the book they've got 3 ice cubes of 6 grams each, so you got 18 grams of ice, and we're assuming that starts at 0 degrees Celsius, so right at the freezing point of water, which may be slightly not quite the right temperature for what comes out of your freezer, but it's okay for the purposes of illustration. And then that's put in a jar of soda or something, so pop, soda, Coke, whatever you call it, and it's 1/4 of a kilogram, and it's soda, and it's at 20 degrees Celsius. And the problem says, go ahead and assume that our specific heat number, specific heat C for the soda, is the same as the specific heat of water, and that is a particular number, 4186 joules per kilogram degree Celsius, like that. We also will need the number for the latent heat of fusion for water ice. And that's going to be 334,000 joules per kilogram. Pretty big number, but the latent heat of vaporization for water is even more vast. And then the question about this is, so okay, you put ice cubes in the soda, and then what is the final temperature? Okay, so that's the problem statement. I'm gonna have to switch sheets now. So we start with the same equation we had before. So we're just doing a counting on the amount of heat that is lost by the ice and then gained by the soda, or vice versa. And anyway, the most important part, of course, is this minus sign here. So if you're thinking of the ice gaining heat from the soda, then the soda is losing heat. You could also do it this other way and put the minus sign on the other side. It's okay. You can multiply that by -1. That's fine. It'll all come out the same if you do. All right. So what was the equation for what's going to happen to the ice? Well, first, it's going to melt. So that equation for Q is mass times the latent heat of fusion. And this is the mass of the ice. I'll put a capital I under there. And then what the problem statement implies is that the ice will melt all the way, and then it will warm up and reach some final equilibrium temperature. And so you add to this the normal delta T formula. So mass times the specific heat of water times the temperature change, which would be T final minus T initial. In this case, we know is 0 Celsius. All right, so that's that side. The soda side is a little bit simpler. Put the minus sign there so we don't forget it. So this would be the mass in the soda times the specific heat of the soda, which we're taking to be the same as water. So I'll put a W there. And then you multiply by the delta T. And we're going to do this in the same sense. So T final minus T initial, and T initial from the problem statement was 20 degrees Celsius. Well, we did it. I mean, this is the setup. So let's see where that gets us. So we need to solve for the final temperature, which appears in 2 places here. So we'll try to put all those terms over on one side, and then we'll put all the other terms on the right side. So what have I got here? I've got a mass initial C sub W times TF for that. term there. And then I can go ahead and, this is a 0, so I can go ahead and neglect that term. It goes away there. Let's go ahead and add MSCWTF to this side. So mass in soda, the specific heat of water times T sub F. And it's positive because it was negative over there. And then let's subtract a negative MILF from here. And this is, there's two negatives, negative there. So plus MSCW times a 20 Celsius. Maybe we should have invented a variable for that for compactness, but I didn't. So there we go. TF factors out. And then we just add those two things. In fact, I'll do it in one step. So we'll take this whole side over here, maybe get things switched around, 20 Celsius minus MILF, and then we divide by this stuff, MI plus MS, all times CW. Well, this does give you the answer, and it ends up being 13 degrees or something like that when you plug the numbers in, because we know all these things. We know the mass of the soda from the problem statement. We know the specific heat of water, which appears twice. We have the beginning temperature here. We can look up this this latent heat of fusion for water. You know, that was given also, and then the mass of the ice, the mass of the soda. We know all those things. So this turns out to be, you know, trust me, it ends up being 13 degrees. Oh, but what if, right? So that's oh, really? Is that really the answer? Well, it's kind of sneaky because the problem statement said, it kind of implied that we're going to end up in the liquid phase for that ice. Well, what if you had more ice? So if you don't know that it's going to end up liquid, then you can't set up this equation at the top. You can't just say that all of that latent heat is going to be used up. And there might be ice left over. You might have too much ice and it won't even all melt. So so be careful. So let's do that warning symbol with the triangle and the exclamation point there. So what you should do is you should check the actual values. So check the latent heat of fusion, mass times latent heat of fusion, versus the entirety of the temperature loss from the soda. So what would that be? That would be the entire 20 degrees Celsius down to 0 for delta T times the specific heat of water times the mass in the soda. And so if this ends up greater, so if the fusion amount of energy you need to make solid to liquid is greater than this temperature raised to 20, then in fact the ice didn't melt. And so you're going to be stuck at 0 Celsius, and you're going to have a mixture of ice and water, ice and soda at the end. So this is in general what you should do. So you go kind of stepwise. Let's go back a page. So if you started in this problem, we start with the ice at 0 and the soda is at 20. And the question is, how much ice and water and soda is there, and where is the balance? And it could land, as in the problem statement, could land in the liquid phase, but it could also land halfway through the solid phase. And that's a continuum. It's 100% solid at the left end, but it's 100% liquid at the other end. And then in the middle, it's a continuum. So some ice and then some liquid. So you could end up with a mixture of solid and liquid, and in that case, it's going to stay right there at this 0 degrees Celsius phase. Same type of thing for vaporization, but of course it's totally the same. in every respect. It's the same. All right, so that's how you do those types of problems. What is the final temperature?